We're going to have a quick chat about trees. There's two more trees slides we're going to go through, which are AVL trees today and 234B trees tomorrow. AVL trees today are a form of tree that is less space efficient, but easier to rebalance, is the crux of it. So why we're learning about this is because um, typically a rebalancing cost is ON worst case, because you have to traverse, in the worst case, the longest branch of the it's ON worst case because you have to traverse like kind of everything. But we want to find something that's like log n when it comes to rebalancing. So we're going to be looking at what an AVL tree is. We're going to be looking at examples of this tree, and then we'll look at some pseudocode. So I hope those birds aren't annoying. Probably can't hear them. So firstly, AVL trees are trees that fix imbalances as soon as they occur, which I guess is probably what you meant by a self-balancing tree before, but it aims to have the tree reasonably maintain balance with an O log n cost. So this doesn't mean that rebalancing is free. It means that there's a method we can use to make rebalancing regularly more often and manage rebalances. Remember, there's a sense of a weight balance in a tree, and there's a sense of a height balance. The way AVL trees work is really quite straightforward. I've lost my paint file. That is that normally on a tree you have like a node, right? And you got a node with all these different children, and as you know, the data structure. That's good. I'm very happy with the birds. I've lived in residential metropolitan areas for a while. So you have this kind of tree, right? And each thing is like a node value and it has two children. But what an AVL tree does is it actually stores some extra stuff. So it makes all of these little nodes just a little bit more chunky. So all of these nodes are going to store some extra memory. And that memory is going to be used to help us actually rebalance the tree more efficiently. So the general method we follow is that we store information on each node about the node or the subtree or the tree's height and balance. So each tree has a kind of a persistent sense of how balanced it is. And then what we do is we do repairs on tree balance. We do local tree balance repairs, not on the overall structure. And it's called AVL trees because of the two people that kind of invented it in the 60s, a long time ago. You know, Georgy Adelson-Velsky and Evgeny Landis. I never had to say those out loud. So an AVL tree method says that a tree is unbalanced, right? A tree is a height unbalanced, you could say, when the height of the left subtree minus the height of the right subtree is not equal to 1. Now, we kind of talked about that the other day, because the height of a subtree is the number of further steps you have to take to the bottom. So when you look at a tree like this, and let's just steal this and dump it in paint here. Where's something more friendly to paint? Why are these all so janky? So when you look at like a tree like this, you could actually figure out what the height is of all the subtrees. So what's the height of this tree here? Well, it's 0. Now remember, when I say tree, every node, every subtree itself is a tree, right? Remember, because it's a recursive structure. So that tree's height is 0. This tree's height is therefore 0. This tree's height is 0. This tree's height is 0. This tree's height is 1. This tree's height is 2. And this tree's height is 3. Okay, so the red is all the heights associated with these trees. Now here's the interesting question. Let's, on each node, figure out what the difference is between the height of my left subtree and the height of my right subtree. So in this case, it's 0. So all the nodes with all the trees with no children, the difference between the left and the right height is always 0, naturally. But then what's the difference here? Well, both of its children have 0 height, so this one's height difference is 0. Then we look at this node here. This child has a height of 1. This child tree has a height of 1. This child tree has a height of 0. So the difference here is 1. And then this tree, its left child has a height of 2, and its right child has a height of 0. So its height difference is 2. So the red numbers are the height of these trees, and the green numbers are the height balance difference, right? How unbalanced they are in terms of height. So An AVL tree is essentially storing this information on the node, because remember, every node is itself a tree. That's the crux of it. And then we're going to use this information to actually rebalance a bit more regularly. Now, the logic of it's quite simple. If you have a tree that is height unbalanced, as in the height of its left tree and the height of its right tree differ by 1, then you can just use rotations to fix this. So if you have a particular tree, i.e. a node in a subtree or whatever, and the left side is too deep, it's too tall, you can fix it just by rotating the root right. And if the right subtree is too deep, you can just fix it by rotating the root left. And that kind of makes sense, because if you have a structure like this, you can see here, this is height imbalance because it's the difference between the two children's heights greater than 1. We could fix this just by rotating it right. Now, how do we rotate right again? Well, I'm just going to like drag these down a bit. This is going to get real ugly. But we rotate it right by bringing the left up and around. I'm just going to rub these out, and I'll just show you. How do I make my thing bigger? Great. Yeah, so you'd kind of... this would be a rotation, if you remember this from the tree rotation lecture. Right, that's where we'd end up after the rotation, and the tree would be balanced. So remember that a rotation, like, I want to rotate the root. So to rotate the root, I kind of grab it and I twist it to the right, because it's a right rotation, which brings the left up as the new root of this subtree. Because remember, this here is a tree, but it's also like a subtree. And then I would have to recalculate some of those heights. So that's the way an AVL tree works, is it keeps track of how balanced each node is. And if at any point this condition is not true, it undergoes, the root itself of that subtree undergoes a left or a right rotation. Now, normally, if you wanted to rebalance based on a particular node, this process would be ON, as you would have to traverse all the nodes in the subtree to figure out the height of it, right? But by storing it, we're doing what we talked about, amortization, which is basically doing some work in advance. And what we're doing here is we're actually sacrificing memory for performance. So we're actually making our tree need more memory, more RAM to be built, but it's going to be a little bit faster. Waleed says, do we only have to rotate it once? Well, yeah, so as Jeremy says, it depends how unbalanced it is. So essentially, you would end up doing rotations until that height difference went down to 1. So at the moment, the height difference was 2, so we did one rotation, which will bring it down to 1. Whereas if the height difference was like 10, we'd have to do quite a few rotations. So you'd often be rotating it until it's balanced. Yeah. That's if you want, yeah, that's, yes. Why is it greater than 1? Well, that's because we talked about this last week. Trees will always have some slight height imbalance with them. So for instance, this subtree here, if you just focus on this subtree, it's technically balanced. Because, like, what do you expect? You can't just make 2 nodes out of nowhere. Like, it's technically balanced. That's why this here is 1, because the height difference with it is yeah, that. So does the height diff change by 1 each rotation? Yeah, so after you do the rotation, you would then have to change the height difference. Yes. So that's the thing about this structure, is there's a lot more work involved in like the setup, right? So if I was to then rotate this, sorry that this is such like an ugly, let me just pull this up here. Oopsie daisy. This is so ugly. But yeah, so after you rotate it, you could imagine that some of these need to be recalculated. Okay? Because not all of this is true anymore, in the sense that, like, sure, this node here no longer has the correct height balance, the height difference, but all these ones do, and neither does this one. So in this case, these two would need to, well, and this one too, potentially, they would need to be recalculated. So there's just a little bit of a calculation step involved. Now, funnily enough, I didn't actually intend to draw these on the tree in these colors. I just picked two colors I liked. So this is really convenient. Um, but this is kind of how these trees work, is that you store the height. Typically, you store the height. You store the red number on the node. So if you have a node, you actually store that red number on there, because the height's like an empirical piece of information. The green one, you could store it, though generally it's calculated, because the balance of a node, the balance of a subtree is totally dependent on the children's height, which generally you can kind of consider as a constant time operation, because no matter how big the subtree is, getting the balance on a particular node, you just need to look at the two immediate children, to figure out what the balance is, what the difference between those heights are. So generally red's stored on the node, green is can be stored on the node, though then there's more to maintain. And again, it's only a constant time performance improvement. But yeah, green's usually calculated. So here is an example. This is a great little example, and I might drag this. So let's say we have, let's try and do this kind of tree here. So we're gonna this is our AVL tree. The 6 is the number that's being inserted here. Now, before the 6 is inserted, this tree probably looks slightly different, because you can see that these are the numbers after 6 has been inserted. So I don't have the tree before. Oh, I do. It's right here. Sorry. Sorry, I was just double checking something. So this is kind of the tree we start with. You just jostle these around. Sorry for the waggling of everything. So here we have our tree at the start, and you can see all the numbers make sense. All the leaves have a height of 0, all the, it all kind of trickles up 0, 1, 2, 3, all the way up to the root. The root has a height of 3, and you can see that the green is the balance on the tree, the height balance on the tree. So the current, everything kind of falls within this one difference of height here. Because you can see this is 1. So this is 1 because its children has, what would you say? That's quite perplexing. Oh yeah, that makes sense. I mean, yeah. I mean, I probably simplified the math a little bit when we did that example previously, but this kind of makes sense, because if green's your height balance, like the difference in it here, you can see this one as 1. I was just kind of summing up the numbers, but with the green as 1 here, makes sense because one child here exists and the other child doesn't. So it's got an imbalance of 1. And then here, same kinds of things. You get this, but the point, sorry, I'm just reading the questions. Jed says the -1 means always use left minus right. Well, it doesn't really matter, because when you actually look at the determination of whether it's balanced or not, you look at the absolute value of it. That's kind of evident here. So it doesn't really matter. Like, this is just for demonstrative purposes. Often you would want to keep it as a negative, because the negative would help you understand whether the left or the right is bigger. Convention would probably be left minus right, and the signedness of that would definitely help you derive some information. But when you actually do the check, you would check the absolute value of it. If we try to insert a 6 into this tree, though, I want you to pay attention to how some things differ. So the first thing you'll notice is that all the heights on this right subtree of 5 go up, because there's another node there. So the 6's height goes up by, well, the 6 gets added, and its height's 0. So the imbalance on the node above is now 1. Because now it has one child on one side, no children on the other side. Same thing as you go up, the height of 8 increases, so its imbalances too. But you'll also notice here that the height of this subtree, this entire subtree here, was 2, and it's still 2. So the actual height balance of the overall tree has not has actually improved. So this is why in the slides you see at the start it says, where is it? Do repairs on the tree balance locally, not on the overall structure. Because rebalancing the entire structure, right? It's like one of those things like trying to keep your kitchen super tidy. It's just always going to get a bit messy. The way it doesn't get messy is if you just don't use it. And there's no way to avoid that, because you might look at this tree over here and think, that doesn't look perfectly balanced for me, because we've kind of got something here and something here, which is, two level, like, ideally we would have found a way to kind of put this 3 like here, or reshuffle things around so it was perfectly balanced, right? Because remember that rule we kind of had in some instances was like that. But doing these kinds of rebalancing on the whole structure are really complicated. So we just focus on things locally. So we just look at, say, this, and we say, is that rebalanced? Yes. And then we look at this, and we say, is that rebalanced? Yes. And then we look at this, and we say, is that rebalanced? And then we look at this, and we say, is that balanced? Sorry. And so forth. So what's interesting here is that this tree is considered balanced. This tree is considered balanced. And the height of those two only differs by 1, so this tree is considered balanced. When we add the 6 here, the interesting thing that happens is the overall balance of the tree actually gets better, because the heights of the two subtrees are closer, because they're both 2 now. However, the right subtree, if you look at this one in isolation, its balance has actually gotten worse, because it's now kind of like a linear line. So it needs some rebalancing now. And the way you would rebalance that is you would rotate it by the right. So if you find a tree, remember, because this 876 here is a tree, if you find a tree that is imbalanced, because this green number is bigger than 1, then you will rotate the root typically to balance it. So in this case, you'd rotate the root by rotating 8 to the right, because again, you want to grab 8 and you want to twist it to the left to bring 7 up here. And then what that tree would look like after you rotate 8 to the right is it would, well, that one's pretty intuitive, because as we said, rotating is kind of easy if there's not 2 children. It would just look like that on the right. So now this tree is actually, this tree is height balanced. And this is kind of the thing, I know I've said this like 4 times already, but I really want to emphasize this, is that an AVL tree structure is not about making sure your entire tree is perfectly balanced at all points. It's about every time you look at a particular subtree in isolation that it is height balanced. Because we actually made the tree less kind of like, the tree has different heights of the subtrees now, after the rotation. So it used to be kind of more even here. See that 0 there? So this 0's gone to 1 now, but the point is everything in the tree is no greater than 1, has an absolute value no greater than 1. So that's kind of why we like these trees. The pseudocode here is a little bit heady, I guess. I kind of find this stuff a little bit hard to wrap my head around sometimes. I usually sit down and think about it for like 5 or 10 minutes, but essentially this is an insertion algorithm. So with a lot of kind of trees that have rebalancing properties, the actual balancing occurs during insertion. And in this case, you can see that if you try and insert into an empty tree, it creates a new tree. If you come across the item in your tree, you just return, because it's a set, like most of these trees are sets. And the general structure here is kind of, if the item's less, then you go left, and if the item's right, then you go right. So fairly straightforward recursive tree structure. What you will notice, though, is that this kind of follows the postfix style, where you explore the left, then you only explore the left or the right. So it's not really like it's not a traversal of the entire tree. It's not a search. You're just doing an insert down a chain. But you see that we actually do go all the way down to the bottom before we do our stuff. So these recursive calls to the function itself will keep happening. So what actually happens is, if you have a tree like this, and you say, I want to insert the number, there's not much space to insert numbers, insert the number 9 into, say, this tree over here, then you start at 5, you go down here, you go to 8, and then you go here to null, And now at this point you start executing the rest of the code. So you do the entire like traversal down, not searching the whole tree, just looking for the spot to insert it. And then once you get to the bottom, that's when you actually insert it. And that's where you then do the unwinding. So all the rotations actually happen on the unwinding. So you know how this tree, we rotated this tree before after the insert? That's what happens. You insert the 8 and the 7 and the 6, and then as you unwind, you're adjusting what these values are, and you're adjusting the tree structure by doing some left and some right rotations if you need them. And that's why you'll see here that you find the actual node you want to insert into, you find the heights of its left and right subtree, and if those heights are they differ too much, then you're going to rotate left, and if the heights differ too much in the other direction, you're going to rotate right. So in this case here, you can see that the R height and the L height are just the other way around. How do you find height? Well, with an AVL tree, the height's already stored on the subtrees themselves. So if you were to actually build an AVL tree from scratch, the very first node you insert would have, like, I'll try and demonstrate this loosely. The very first node you insert, like here, if that's like a 4, you would actually have the height attached to it like that. And then when you insert, say, a 3, and you put that there, its height would be 0. But remember, the way insert works is you go all the way down to the spot you want to insert it into, and as you unwind, you clean up the tree. So as I insert the 3 and then I unwind, I would end up replacing this 0 with a 1 now. And then if I insert a 2 or something, I would start here and go down. I would find the spot to insert it. It would have a height of 0. But then as I unwind from this recursion, I would have to update the heights of what's above here. Now, naturally, in this particular example, I would also be doing some rotations as well. Because like if you did this, you wouldn't just like adjust the heights as you unwind. You would actually rotate 4. You would right rotate it. So you would end up bringing 4 like down here like that. And they would join up there. Well, he says, I don't fully get the code on line 14. Why do we do an item greater than data tree left? It's a good question. Just reading a question. Why do we do that is the right line. Okay, yeah, I see the line. Then rotate left and rotate right. That's a good question. This kind of comes back to the double rotation stuff, and I was actually hoping to include some. I know James mentioned it. I don't have a great example of this. Someone pointed out to me today that I should probably include it in the slides, so I might just have to go and include it after the fact today, and just make a reference to it next time. But I'll try and give you an example of when this is applicable here. Because I don't think it'll be easy without like a clear diagram, and I'm just conscious of time. So hold your thought on that one. I'll add something to the slides so it'll hopefully make more sense, something more diagrammatic. But the actual good example would be inserting into the subtree that goes left, then right of left. Sure. So let's maybe we can do this one really quick. See how we go with it. I don't like making trees up from scratch, but let's go. So let's say we have a number here that's 5, and then we have one here that's 3. So this AVL tree would have a height of 1 and a height of 0 here. Though if we inserted, just following James's comment, that goes left and go right. So if we then inserted 4 into this one, and we follow the algorithm, if item is greater than data tree left trees rotate left. Yeah, I'm just looking at the clock. Let me put something in the slides about that, and we can reference it at the start of the next lecture briefly. So if you are watching this later, just check out the 234, because we'll talk about it very briefly at the start. Yeah, that's what I mean. There's a bunch of animations. I don't want to draw this out crappily on Paint. I can just show you. I'll find something and put it in the slides really easily. The last thing I want to talk about, just conscious again of time, is the AVL tree performance. So we kind of hinted at the fact that AVL trees store more information, and because of that, it's a little bit more memory intensive. But the idea is that we should have an improved, it doesn't cost as much to rebalance because we have all this metadata available to us. So the average and worst case search performance for an AVL tree is O log of n, because, well, most trees are O log of n, right? Like you just kind of go down one path. It's nothing really particularly new. There is a finite amount of time you need to spend on maintaining the height data of each node. There is a finite amount of time you need to spend rebalancing locally when there's an imbalance. So the actual maintaining of that number next to the tree, as well as the actual rotations, because sometimes there's one rotation, sometimes there's two, that takes some time. But the thing about these is that they're often much closer to constant time operations in terms of like, it doesn't really get much more complex the bigger the tree is. So when we say finite amount of time, what we're saying is that the actual cost of these operations won't appear that dramatically when it comes to your big O notation, because they're often going to be, like checking the height of the two subtrees is like a constant time operation, but it still does take time. So it's negligible in many circumstances, but something you need to be aware of. And what it always ensures is the trees are height balanced. That means that the subtree's heights only differ slightly, but it doesn't guarantee weight balance. So this is a really important thing about AVL trees, because remember we have this idea of height balance where the heights of the two subtrees are the same, and we have an idea of weight balance where the number of nodes in the two subtrees are the same. So last week we talked about partitioning a tree, which is a way to try and improve the weight balance, where you pick like the middle, the median sized entity, and you bring it up to the root, which restructures the whole tree around it and hopefully makes it weight balanced. AVL trees focus on height balance. So this tree you see at the bottom here, this is actually a height balanced tree, and this is what an AVL tree tries to maintain, but you wouldn't exactly call this a weight balanced tree, would you? Because you've got, on the left of the root, you have 7 items, and on the right of the root, you have 2. But it is a height balanced tree because the height of the right subtree is 1, and the height of the left subtree is 2. Like the height of this green circle here is 2, and the height of this green circle here is 1. So the root considers its tree height balanced. That's the crux of that. Well, it says, if time allows, could you tell where having a height balanced tree is more beneficial to performance compared to a weight balanced tree? That's a great question. So a height balanced tree gives you a lot more control. It gives you a lot more consistency in terms of like search performance, because if your tree's not height balanced, that essentially means that different things you look up will have different traversal times. So inserting, deleting, searching can be very inconsistent, because you might have like 10 nodes on this subtree, or you might have 100 nodes on this subtree and 100 nodes on this subtree. But if one of them's balanced, then it's log n, and if one of them's not balanced, it's on. Like it's O log n and on, just like we looked at when we first did kind of the tree stuff. So it essentially ensures that your performance is more consistent. I don't want to say better, because as you move things from one tree to another, they're both gonna balance out a little bit. It will be on average more performant, but it adds a level of consistency. And on the flip side of that, Lewis says, and you've kind of followed this up, surely weight balance doesn't matter that much if it's height balanced. Isn't it just the max difference of one lookup? So that's a great question. So essentially what I just said probably makes sense, and then the obvious thing that follows is like, why does weight balance matter? I won't lie, it's something I haven't given an extensive amount of thought to or read up on, but the obvious thing that comes to my mind from some experience I've had, and there might be more, is that the problem with weight imbalanced trees is that they have a tendency to become height imbalanced a little bit quicker, because say if you look at this tree here, which is weight imbalanced, anytime you add a number that's less than the node, it's going to start growing out its height a lot quicker than this one, which still has some stuff to fill up. So I know at a glance that weight imbalance will tend to lead to height imbalance trees as well. Obviously, there's no real memory issue here because the way we store trees is like as a linked structure. So like, there's no contiguous memory. We can just create more heaped memory anytime. But yeah, it would definitely create some issues when it comes to rebalancing, because a heavier side will grow quicker and in different directions. So if your tree is weight balanced to start and height balanced, as opposed to height balanced but not weight balanced, then you'll probably see less anomalies with how it grows. But yes, generally height balance is probably a lot more important. Yeah, that's correct. So, yes, performance is mainly dictated by height, but poor weight balance increases the volatility in the height, leading to volatility in performance. Yeah, I guess so. I mean, that's just my answer to it. Again, I haven't actually spent much time thinking about the impact of a weight imbalance tree, so there might be some other things I'm missing. So feel free to chat to your tutor about it, or if anything comes to my attention, I'll let you all know. Just 358. So originally I wanted to talk about this on Thursday, but GDB took a little less time than I thought, so I wanted to add some stuff about the double rotation, so I'll add that in between now and Thursday. I just didn't have time because I didn't want to talk about it today. Well, I didn't want to do these slides today, but that's cool. I'm glad we did because we'll have more time on Thursday. I don't think we have any code examples of AVL trees in the lecture code, but there'd be tons on the internet. We don't like a lot of things in this course. There's QR code, thank you. There's a bunch of things we talk about in this course that like sometimes we don't really expect you to necessarily always put into practice. We're going to see this a bit when we do graphs next week and the following week after that. Like, there's some things you're not going to code much in the course, so we talk about it very high level. There's some things we expect you to code a lot, so we talk about it low level. And then there's some things which are we want you to code, but it's a bit of a challenge, so we try not to just lump the code in front of you. That's kind of why we give you the tree code, because often trees we ask you to build might be a little bit more complicated, and we want you to glue things together. But no AVL tree code we have in the lectures at the moment. But thank you, everyone. We'll chat about the other types of trees on Thursday. We'll probably chat about the assignment too. It'll either come from me or Kevin. We'll see how that goes. And other than that, thanks. That's all. So thanks to James and Kai for hanging around in the chat and just sharing some thoughts throughout. And have a great day, everyone.